Welcome, curious minds, to the deep dive. Today, you and I are about to embark on a journey that, well, it might just reframe everything you thought you knew about the universe's beginning.
It's definitely a perspective shift.
Right. Forget the familiar story of an instantaneous, violent explosion from some tiny, infinitely dense point.
Singularity problem, yeah.
Exactly. Instead, imagine a universe that started not with that cataclysmic bang, but with something more like a profound, almost imperceptible whisper. A gentle, rhythmic fold in the very fabric of time itself.
It's a concept that really plunges us into the deepest questions, doesn't it? What is time? What is space before there's space?
It truly is. We're moving beyond the idea of an abrupt, singular event to a process that's, I think, far more nuanced, dynamic, and, well, you could argue, elegantly self-contained.
It redefines the initial conditions for everything that follows, fundamentally.
Absolutely. So our mission today is to take a real deep dive into this revolutionary cosmological framework. And look, this isn't just some minor tweak to existing theories.
No, not at all. It's foundational.
It's a fresh, comprehensive perspective on the universe's origin, the nature of cosmic inflation, a big one, and the fundamental underlying structure of the cosmos itself. We're going to systematically unpack this model, layer by layer.
Starting right from the beginning.
Yeah, from its initial smooth time concept through how all the physical properties we know emerge, right up to its surprising, intricate, and critically, its testable predictions.
Which is key. It has to be testable.
Totally. We'll see how it challenges but also reinterprets the standard narrative, all while diving deep into the mathematical and physical underpinnings that make it, frankly, so compelling and coherent.
And our insights today, they're drawn from a fascinating convergence of cutting-edge research. Our main sources include A Gentle Fold into the Big Bang, which sort of lays out the core concept, this non-singular origin.
Okay.
Then there's Cosmic Quakes, From Calm to Inflationary Boom, which really gets into the mechanism of inflation or its replacement here.
Right, the quake idea.
Exactly. Plus, Fractal Cosmology, a new view of the Big Bang, detailing the geometric side of things, the structures it predicts.
Fractals. Interesting.
And finally, The Folding of Time, a unified cosmology, which provides the overarching theoretical framework, tying it all together.
So, a solid base of research.
Definitely. Together, these sources lay out a cohesive, testable alternative to the conventional Big Bang theory. They offer a compelling, really detailed explanation for how our universe could have begun and then, majestically evolved into what we see today.
Okay, let's unpack this then. Let's start at the very, very beginning, before anything we recognize as physics even existed. In this model, the universe's genesis is truly a gentle fold, not that violent bang. That's a foundational departure, isn't it?
It is the cornerstone, absolutely. The conventional Big Bang model confronts us with a mathematical singularity, this infinitely hot, infinitely dense point from which everything supposedly exploded.
A point where physics just breaks down.
Right. Our current laws stop working there. We have to postulate unknown physics or invoke quantum gravity without a clear picture of what that even means at that point. This new framework, though, proposes something entirely different, something more primordial. A pre-fold universe of smooth time. It completely bypasses the singularity.
Smooth time. Okay, that sounds almost meditative, or maybe completely alien. For us, for you listening, how do we even begin to conceptualize a universe in a state like that? What does smooth time actually mean fundamentally?
Okay, imagine it as a global phase field. We denote it mathematically as the theta. Now, in this initial primordial state, the crucial point is there are no gradients in they.
No gradients, meaning no differences from place to place.
Exactly, no differences at all. Now, what are the implications of no gradients? Think of it like a perfectly uniform, featureless, scalar field permeating everything, except, crucially, there is no everything yet. This translates directly to no localized energy, no discernible temperature, no established geometry, just undivided continuity. It's a state utterly devoid of the usual physical properties we associate with existence.
So no up or down, no hot or cold, no inside or outside. It's not even empty space because space itself hasn't emerged yet.
Precisely. It's a state of pure, undifferentiated potential, not even a vacuum as we understand it in quantum field theory, which is actually buzzing with virtual particles. This is less than that.
So it's not a supercooled, extremely dense vacuum state like some inflation theories might suggest. This is a step beyond that, almost pre-physical, where density or temperature are literally meaningless concepts.
That's it, exactly.
My analogy, then, for you listening, might be to imagine a perfectly still, utterly undifferentiated ocean, Not just calm, but without any waves, any currents, any boundaries, any distinctions whatsoever. Just an expanse of absolute featureless calm. Not even a surface or depth. It's just...
Precisely. It's the ultimate tabula rasa. A canvas before any brushstroke, a melody before any note is played. There's no information, no local variation, and therefore no discernible physics. This is where the universe waits, essentially, for its first act.
Okay. And if that's the pre-fold universe, this state of pure, undifferentiated potential,
Yeah.
what is the first event that kicks everything off? If it's not a bang, what's this fundamental shift that brings physics into existence?
It's what the sources call a soft fold. Instead of a violent explosion, the initial event is this gentle foundational fold of the phase field into what's mathematically described as a half-lock, or simply a polarity.
A half-lock.
Yeah.
Like splitting into two.
In a sense, yes. It's the simplest possible differentiation. Think of it less like a rupture or chaotic burst, and more like a subtle, almost imperceptible structural shift in the underlying phase field. Imagine our perfectly still ocean suddenly forming a single, continuous, gentle crease across its entire expanse.
And this gentle fold, this soft shift, immediately introduces something absolutely critical. A small, nearly uniform phase gradient across the entire field.
Yes. That's the trigger.
This gradient is the foundational shift from that undivided continuity you mentioned.
Yeah.
This is where physics as we know it genuinely begins.
Absolutely. Because with this gradient, the very concept of motion itself is born. Now, in this framework, energy isn't some external input. It's intrinsically defined as phase tension. Mathematically, this is expressed as axi equals half v. That's the energy density. Its density is a coupling function is the gradient squared, and v is the potential energy.
Right.
The moment that phase gradient appears, even if it's incredibly small, and uniform motion exists. It exists as the inherent realization flow of that phase tension. It's like the universe's internal drive to dissipate this newly formed differentiation, to smooth itself out again.
And this is a huge distinction. Motion doesn't originate from things moving within a pre-existing space, but from the continuity of time itself folding, and thereby creating differences and tension. It's the universe itself acting to undo that tension.
That's exactly right. This is a fundamental rewiring of our intuition about motion. Motion isn't about particles traversing a landscape. It's the landscape itself undergoing a dynamic process of tension and release.
Wow.
Think of ELA as the measure of how quickly the phase field changes across space, and theta dot, its time derivative, as how quickly it changes over time. The term represents the kinetic energy, the energy of this motion or change within the field.
Okay.
And Vla is the potential energy stored in its configuration, like energy stored in a stretched spring. So the universe is essentially a self-organizing system where the engine of activity is built into its very fabric rather than being driven by external forces or particles.
So motion is a direct consequence, a result of this initial fold and the tension it creates.
Okay.
And what about space and geometry? Do they come into existence before something like gravity? That feels like a very different sequence than usual.
Indeed, it's a crucial reordering. Geometry emerges only after these phase gradients appear. It manifests as boundaries or domain walls within the phase field.
Like the edges where the fold is sharpest.
Exactly. These aren't solid walls, mind you, but regions where the phase gradient is strongest, creating discernible distinctions. And once you have these distinctions, these fundamental shapes, the concept of extension then becomes what we recognize as space.
So the divisions create the sense of extent.
Yes. And gravity, in this profound sequence, is not a primary force. It is the curvature that appears after these phase gradients are already present and geometry has emerged from the phase field.
So geometry first, then space, and then gravity. That's profound. It implies gravity, as we understand it, is more of an emergent property, a secondary effect of these fundamental phase dynamics, rather than a truly primary force that existed from the very first instant.
Precisely. It's a consequence, not a cause, in the very beginning. The mathematical connection is clear. This curvature, which is what we perceive as gravity, is sourced by the stress-energy tensor within Einstein's equation.
Okay, the stress-energy tensor of the phase field itself.
Yes, specifically Gin is proportional to Team. This tensor encapsulates the energy and momentum of the phase field itself, and it's this energy and momentum that tells space-time how to curve according to general relativity. So the dynamics of the phase field directly orchestrate gravity, rather than gravity being an independent actor present from time zero.
And what about temperature? If the universe started in this calm, cold state of smooth time, when did it get hot? Because the Big Bang we know is inherently hot.
Mm.
How do we get from that infinite calm to the scorching temperatures of the early universe?
Right. Well, temperature is initially undefined because, as we discussed, there are no folds yet, no mobile quanta, no localized energy packets to even measure a temperature.
Okay, so cold isn't even the right word. It's just temperatureless.
Temperatureless is a good way to put it. The universe effectively begins cold, only in the sense that there's no thermal energy. It only becomes hot as this fold cascade process progresses. Each new fold, each new boundary stores and then releases energy, gradually building up the thermal energy density, loading it into radiation and plasma.
So the heat is generated by the folding process itself.
Exactly. This is crucial because it directly bridges the gap from our gentle fold origin to the hot Big Bang conditions we infer from observations like the CMB without needing an infinitely hot singularity right at the start.
So the initial state is cold, gentle, profoundly uniform. Then it begins to fold, creating tension, motion, geometry, gravity, and then we arrive at something that sounds far more dramatic, the cosmic quake. That's a really evocative metaphor for inflation. This is where the universe transitions from that quiet hum to a thunderous roar, right?
It's an exceptionally apt analogy, yes. Imagine those very early dynamics. The phase field is nearly uniform across its entire expanse. The gradient term is incredibly small, and the potential Wells V are extremely shallow, like tiny dimples in a vast sheet.
Okay.
This means the early universe experiences these gentle, slow oscillations. Think of tectonic plates under immense but uniform stress, just sitting there, humming, but not yet slipping. Energy exists as a low-tension hum, feeling cold, calm, and exquisitely coherent, exactly as you intuited earlier. This is the prolonged pre-quake strain, a period of accumulating subtle tension.
But just like in geology, stress builds up until something has to give. It can't stay like that forever.
Exactly. This is where the fraction cascade comes in. Each subsequent rational lock, for example, moving from the initial half-lock polarity to maybe a U-lock, then perhaps a one-lock, and so on, adds more and more boundaries to the phase field.
What exactly is a rational lock? Are these like stable configurations?
Precisely. Imagine the global phase field having preferred stable states, much like harmonics on a vibrating string or resonant frequencies in a drum. A half-lock is the simplest polarity, like positive-negative. A O-lock could be visualized as a more complex, maybe triple-fold division, perhaps related to hexagonal symmetry. These aren't just abstract numbers, they are inherent, stable, geometric configurations that the phase field naturally adopts based on its internal dynamics and the shape of its potential energy landscape.
Okay, so it clicks into these stable states.
Yes, it settles into these minima, and crucially, these boundaries, these domain walls between regions locked into different phases, carry increasing energy. Why? Because the phase gradients sharpen significantly with each new layer of folding. You're creating more complex patterns, packing more change into the same space.
So you're accumulating immense stress, phase tension across these newly formed domains.
Yeah.
Like geological strain building in rocks over millennia before a major earthquake.
That's the perfect analogy. Mathematically, this is explicitly shown in the energy density equation, plus V. More folds mean sharper gradients, a larger term, which directly translates to a rapidly increasing energy density. The potential energy V might also change, but the gradient term becomes dominant.
So the calm rhythmic hum is slowly but steadily turning into this building pressure cooker. What happens when that pressure, that accumulated phase tension, reaches a critical breaking point? This sounds like the point of no return.
That's precisely the quake moment, the inflationary boom. At a critical threshold, multiple rational folds, or locks, occur nearly simultaneously across vast regions of the phase field. It's like many fault lines slipping at once.
A cascade.
A cascade, exactly. This is the universe's fault snapping. The immense accumulated phase tension and stress release explosively, driving rapid expansion and violent restructuring of the nascent cosmos. This is the phenomenon conventionally called cosmic inflation. But here's the punchline. It's not driven by some arbitrary, unknown inflaton field added just for this purpose.
Right.
It's an intrinsic dynamic response of the phase field itself, reacting to its own internal stress.
So inflation isn't some mysterious external field pushing things apart. It's the universe basically reacting violently to its own built-up internal tension from these folding processes.
Yeah.
That's incredibly elegant. It feels much more self-contained.
That's absolutely right. Mathematically, this corresponds to a critical bifurcation. This occurs when the derivative of the potential, V, which you can think of as the force driving the field, crosses the stability threshold.
Like pushing a ball balanced on a hilltop?
Exactly like that. Imagine our phase field sitting in a very shallow valley, a minimum of V. As energy accumulates from the fractional cascades, this valley subtly shifts, becoming unstable, maybe flattening out, or even turning into a peak. When V crosses that threshold, it signifies that the force on the field changes direction dramatically. This causes the phase field to run incredibly quickly between its potential wells, seeking a new stable state. This rapid, coherent movement of the field across the entire cosmos dramatically alters the energy landscape and drives an exponential release of energy, primarily kinetic energy of the field itself, which translates into expansion. This rapid exponential release of energy is the very definition and observable characteristic of inflationary expansion as we infer it from the cosmos. It's a phase transition in the field's behavior, transforming stored potential and tension into kinetic energy of expansion.
And what happens after this monumental cosmic quake? Has it truly wiped the slate clean, smoothed everything out perfectly? Or are there subtle echoes, faint memories of that calm, pre-quake strain still resonating within its structure?
That's a great question. Once this cascade shakes out, the intense rapid expansion has primarily converted most of the released energy into free radiation, a scorching hot plasma of photons, neutrinos, and other relativistic particles. This is why the universe after inflation looks hot and, on smaller scales, quite chaotic.
Right, the hot Big Bang we know.
Precisely. However, and this is a crucial point, its large-scale geometry remains remarkably smooth. This smoothness isn't lost, but is actually reestablished or reinforced because the quake, this rapid expansion, effectively redistributed the tension and energy incredibly evenly across the vastness of the now much larger cosmos. It irons out wrinkles on the largest scales.
So it homogenizes things.
Exactly. This process directly and seamlessly leads into the radiation-dominated expansion described by standard Big Bang thermodynamics, which we have observed and measured with such precision via the CMB and other probes.
So was the universe born smooth and rhythmic, or was it a boom? Listening to this, it really sounds like one of those situations where the answer is genuinely both.
Exactly. You've nailed it. At the very, very beginning, in the deepest sense, it was profoundly smooth, calm, and oscillatory, that pre-quake strain, a universe of pure potential just humming along. Over cosmic time, the process of fractionation, the locking into rational phases, added stress, but rhythmically and coherently at first. Then, at a critical threshold, this accumulated stress transformed into a quake-like cascade, which is inflation, the boom, a rapid violent release. And then after that violent rapid expansion, it's rhythmic again, but now at a much hotter, vastly more energetic baseline, entering the familiar hot Big Bang era, cooling and expanding. So the universe wasn't born in an instant bang of pure violence from a point.
Right.
It was a calm oscillation that quietly built stress, then shook itself out in a boom-like cascade of folds, much like a geological earthquake that brews for ages before its powerful yet ultimately homogenizing release. It's a continuous, interconnected process, from calm to stress to boom, back to rhythm, but a different kind of rhythm.
That's an incredible, detailed story of cosmic origins, shifting our perspective so dramatically. Now let's address the elephant in the room. How does all of this fit with what we already know about the universe? This model can't just throw out everything we've meticulously measured over decades.
No, absolutely not. That would be unscientific.
It has to reinterpret the origins of those crucial cosmological landmarks. This is where the rubber meets the road for any new theory, right? Does it match the data?
Absolutely. Any viable cosmological model must rigorously account for the highly precise observations we've made. Things like the CMB spectrum, Big Bang nucleosynthesis, large-scale structure. This framework doesn't discard these empirical anchors. It offers a deeper, perhaps more intrinsic explanation for how that evidence came to be. It has to match or even enhance our understanding of these established facts.
Okay, let's start with the big one. The cosmic microwave background, the CMB. It's the afterglow of the Big Bang, an almost perfect 2.725 Kelvin blackbody spectrum. The deviations measured by Cobas were less than 50 parts per million. That spectrum is one of the crown jewels of modern cosmology.
Indeed it is. And this model treats the CMB's near-perfect blackbody spectrum as a non-negotiable empirical anchor. The core thermodynamic processes that lead to that blackbody shape are preserved. The model leaves the spectrum itself essentially untouched.
So the shape is identical.
The overall blackbody shape, yes. What it does alter, potentially, is the higher-order correlation structure within that spectrum, the tiny temperature fluctuations, the anisotropies at the microkelvin level. It suggests they might not be perfectly random, but the perfect black body temperature and shape, that remains, which is a powerful validation point for its consistency with observed reality.
Okay, good. And the timing of recombination, that pivotal moment around 380,000 years after the start, when the universe cooled enough for electrons to bind with atomic nuclei, allowing that CMB light to travel freely.
That timing remains exactly as measured and predicted by standard cosmology. Approximately 380,000 years after the fold cascade finishes and the hot era begins, at a redshift of roughly Z 1100.
Okay.
This is when the photon baryon plasma cooled to about 3000 Kelvin, allowing neutral atoms, mostly hydrogen and helium, to form. Electrons bind to nuclei, and suddenly photons can free stream without constantly scattering off free electrons.
And those are the photons we see today.
Precisely. Those are the photons that, after redshifting for billions of years as the universe expanded, become today's observed 2.725 Kelvin CMB. The model's post-inflationary era must seamlessly integrate with this known timeline, and it does.
Okay, so the temperature, the black body shape, and the timing of this CMB's origin are preserved. What about Big Bang nucleosynthesis, BBN? This gives us the cosmic abundances of light elements like hydrogen, helium, lithium, another incredibly successful prediction of the Standard Model.
BBN proceeds at the standard time as well, roughly 1 to maybe 200 seconds after the fold cascade when temperatures were incredibly high, around 10 billion down to 1 billion Kelvin.
The universe is a nuclear furnace.
Essentially, yes. And this process still produces the known cosmic abundances, about 25% helium-4 by mass, along with those trace amounts of deuterium, heavy hydrogen, helium-3, and lithium-7. The model explicitly states that its reinterpretation does not alter these yields.
Why not? How does it guarantee that?
This is a critical validation point. It means that once the universe enters the radiation-dominated regime, following that cosmic quake or cascade, the thermodynamics and nuclear reaction rates are identical to the Standard Model. The framework accurately describes the transition into this well-understood hot plasma phase. So the initial conditions are different, but the subsequent physics, once that hot state is established, aligns perfectly with standard BBN calculations.
Got it. And those distinctive acoustic peaks in the CMB angular power spectrum, those subtle ripples that tell us the universe is spatially flat and give us insights into its composition, dark matter, baryons, etc.
Yes, the acoustic peaks. These represent the pressure waves, sound waves really, that propagated through the photon baryon fluid before recombination. They leave an imprint on the CMB temperature fluctuations. In this model, those peaks remain precisely where the Planck satellite measured them with incredible accuracy. These peaks encode a huge amount of information about the universe's geometry and content. And indeed, the overall spatial flatness of the universe, the observation that E total is very close to 1, is also preserved by the model.
So all these critical landmarks, the CMB spectrum, recombination timing, BBN yields, the acoustic peaks, flatness, they all stay intact.
Correct. The model doesn't negate the evidence. It offers a new, deeper, and arguably more elegant story for how that evidence came to be shaped in the first place.
Okay, so if it preserves all these core landmarks, where does it fundamentally differ in its interpretation? This is where it gets really interesting. It reinterprets the origin of smoothness and expansion, effectively replacing the standard concept of cosmological inflation. That's a monumental claim.
This is definitely one of the biggest divergences, yes. And it addresses what many see as a significant conceptual challenge in orthodox cosmology. The standard view attributes the observed large-scale uniformity, why the CMB is so smooth, and the flatness of the cosmos, to a very early, extremely brief phase of superluminal expansion called inflation.
Driven by the inflaton field.
Driven by an unknown scalar potential, yes, commonly called the inflaton field. But this field is essentially an ad hoc addition to the standard model it's put in specifically to solve these problems, horizon, flatness, monopolies. But it doesn't necessarily arise naturally from known physics. It feels like a patch to some.
But this new model has a completely different and seemingly more integrated explanation for that rapid smoothing and expansion, right? One that doesn't require adding a whole new hypothetical field.
Yes, a far more intrinsic and, I think, elegant one. In our model, the rapid smoothing and the near flatness arise not from a separate exotic scalar potential, but from the dynamic process of that brief cascade of additional fractional locks, the half lock, followed rapidly by OO and so on, occurring in quick succession.
The cosmic quake again.
Exactly. This dynamic internal process drives the universe's scale factor, AAT, to grow almost explosively, essentially performing the exact job of inflation, smoothing things out, flattening geometry, but without needing an ad hoc inflatant field. The mechanism is built directly into the fabric of time's folding.
Okay, can you walk us through the mathematical foundation for that again, maybe a bit more slowly? How does this internal cascade physically drive that exponential growth and ensure flatness? It sounds like the phase field is doing double duty here.
It is doing double duty in a way. So the phase field obeys this quasi-linear wave equation, plus v is 0. This equation describes its evolution, how it changes in space and time.
Let's break that down intuitively again.
Okay. The first term represents how the flow or current of the phase field is distributed or conserved. The second term is an interaction term. Is this kinetic coefficient basically dictating how readily the field moves or responds is its derivative. And V is the derivative of the potential, representing the force pulling the field towards its stable states or locks.
Okay, dynamics, interaction, and potential force.
Exactly. Now, the key insight here is the conditions during the cascade. The potential V has these minima at the rational phases, asto, etc., and they might be relatively shallow initially, but the kinetic coefficient main is thought to be nearly constant and positive during this early rapid phase.
Right.
Under these specific conditions, the initial folds create low-tension domain walls first, ensuring that the very beginning is gentle and homogenizing, not violent. But then, as more folds rapidly lock in during the cascade, the phase gradients sharpen dramatically. The field is changing very quickly.
The term gets big.
Very big, and the energy density is a half day, plus V. During this rapid cascade, theta dot, the time derivative, how fast the field changes in time, also becomes very large, but remains approximately constant. This unique combination, large here from, but relatively constant, means the energy density becomes very large and nearly uniform across space.
Ah, okay. Large and uniform energy density.
Yes. And a large uniform energy density, dominated by the kinetic terms related to Daction era, naturally drives exponential expansion according to Einstein's equations. This generates the observed flatness and uniformity, providing the necessary exponential growth without needing an external inflaton. It's an intrinsic property of the field's own dynamics during this critical phase transition.
That's incredibly elegant. It's not just a dynamical object, the phase field, but its inherent behavior during this cascade that does the heavy lifting, creating the initial conditions and then smoothing the universe into existence. It really feels like self-organization.
Indeed. And crucially, following this rapid cascade, as the energy stored in the field's motion gets converted and thermalized into radiation, photons, etc., the dynamics smoothly transition into the usual radiation era.
Back to standard cosmology.
Exactly. You recover the standard relationships that govern the early hot universe. The energy density of radiation orid, SIR30 G aura, where G counts the relativistic particle types. The scale factor evolves as AT12 in the radiation era, and temperature drops as T1A. It seamlessly connects to the well-understood hot Big Bang, preserving all its successful predictions after the cascade ends.
So what does this all mean for those long-standing, stubborn puzzles in cosmology, like the horizon problem and the flatness problem? Inflation was originally cooked up largely to solve these.
Right. The horizon problem, the perplexing uniformity of the CMB, how regions that seemingly were never in causal contact would have the exact same temperature, is elegantly explained here. The explanation is that the early global fold was soft and inherently uniform across the entire field from the start.
Ah, because it started from smooth time.
Precisely. The initial phase field was nearly homogeneous globally. It wasn't starting from a chaotic mess of disconnected patches that needed inflation to bring them together and equilibrate. Here, that large-scale uniformity is fundamentally built in, a consequence of the initial undifferentiated state folding gently.
Makes sense. And the flatness problem. Why is the universe observed to be so exquisitely spatially flat today, poised on that knife edge between expanding forever or recollapsing?
The observed spatial flatness, P-total OM1, is attributed here to the nature of the global phase unfolding. This intrinsic global uniformity, especially after the homogenizing effect of the cascade, naturally ensures a large-scale uniform curvature. And the dynamics of the cascade itself drive the curvature towards zero, resulting in flatness. Local folds only later induce the smaller scale structure, galaxies clusters we observe, but they sit within this overall flat geometry.
So these fundamental cosmological problems find natural intrinsic solutions within the dynamics of the phase field itself, without requiring a separate hypothetical influent field.
That's the core argument, yes. It aims for a more unified and less ad hoc picture.
Okay, that was a lot of ground covered, illuminating the conceptual and mathematical differences of this new model. But you promised us an even deeper dive into the mathematical framework, and I know our listeners are hungry for it. Let's really get into the nuts and bolts, the rigorous language that describes this unfolding cosmos.
Absolutely. Let's look closer at the engine room. The fundamental mathematical object describing this entire model is, again, the phase field with its associated Lagrangian. The
Shangmia, the Lagrangian.
Right.
Not just an equation, you said, but the blueprint.
It is. It's the core principle that governs the field's behavior, its dynamics, and crucially, its interactions with space-time itself, represented by the metric tensor bin. In physics, the Lagrangian encapsulates the system's dynamics. Systems evolve to minimize something called the action, which is derived from the Lagrangian. It basically tells us the natural path the system wants to follow.
Okay, for our listeners who might not be deriving Lagrangians daily, can you give us a sense of what this blueprint really tells us about the universe? What do those terms, like the half-gen part, fundamentally represent in terms of the field's activity? How does it drive the story we've been discussing?
Certainly. Think of the Lagrangian as having two main parts, a kinetic term and a potential term. The term half-gen is the kinetic energy term.
Energy of motion.
Exactly. Here, gen is the metric tensor describing the curvature of space-time, and yin represents the gradients of the phase field across both space and time. And I'll run from 0 to 3. So this whole term encapsulates the energy of motion, or the energy associated with the field's dynamism, how it changes from point to point and moment to moment. It's the driving force of the field's evolution.
Okay.
Is a coupling function, possibly dependent on the phase itself, that modulates this kinetic energy. It could affect how easily the field changes.
Okay, and the other part?
That's the potential energy term. VE is the potential energy landscape. You can visualize it as a landscape of valleys and hills. The field wants to settle into the valleys, the points of minimum potential energy. The specific shape of V dictates the stable configurations, those locks, like the phase field can naturally adopt.
So Lagrangian balances the field's tendency to move and change, kinetic term, with its tendency to settle into stable states, potential term.
Perfectly put. The interplay between these two terms governs the entire unfolding of the universe in this model.
And this is precisely where energy itself comes from, right? From these gradients and this potential. It's not inserted from outside.
Exactly. The model precisely defines the energy density, which is what curves space-time and powers everything as arising directly from these phase gradients and the potential. Plus V. This is essentially the energy density component of the stress energy tensor T we mentioned earlier.
Breaking that down again.
Is the energy density. The kinetic term, this is simplifying slightly, it involves both space and time derivatives, describes the energy associated with the field's dynamics, its changes across space and time. And V represents the potential energy stored in the phase field's configuration itself. It's a self-generating energy source woven into the fabric of the cosmos.
You mentioned earlier that the first fold was gentle. How is that claim rigorously grounded mathematically? How do we know it wasn't just a violent explosion from the outset, even within this model?
It's mathematically grounded in the specific assumed forms of V in the initial conditions, near the smooth time state. The claim the first fold was gentle means specifically that the potential V is initially extremely shallow around the starting state, and the kinetic term coefficient is nearly constant and positive.
Okay, shallow potential, steady kinetic response.
Right. Under these specific, carefully defined conditions, the domain wall tension, the energy stored in these initial boundaries, formed by the first half-lock, is very small. This mathematical feature is absolutely crucial. It ensures that large-scale homogeneity is preserved even as these first gentle gradients begin to build.
So it doesn't immediately shatter into chaos?
Exactly. The violence, meaning higher energy density and rapid chaotic expansion, only increases later, as additional fraction locks stack up during the cascade. As more complex folds occur, the gradient term grows significantly, the potential landscape might become steeper, and that's when the energy density rockets up. This precise dynamic delivers the universe smoothly and non-violently into the hot radiation bath, entirely avoiding the problematic concept of an initial singularity.
So the quake moment that triggers inflation, that explosive release of energy, is also mathematically precise, not just a nice metaphor. What does that look like in the equations in terms of V?
It is indeed mathematically precise. The quake moment, the onset of the cascade, is described as a critical mathematical bifurcation. This occurs when the derivative of the potential crosses a specific stability threshold.
The force changes character.
Yes. Intuitively, imagine our phase field settling into one of those shallow valleys, a minimum of V. As energy accumulates from prior slower folding or as the field evolves, the shape of this valley subtly shifts. Maybe it flattens out or a barrier to another deeper valley lowers. When V crosses a certain threshold, it signifies that the force driving the field changes direction or magnitude dramatically. It becomes unstable where it was stable.
The ball rolls off the hill.
Precisely. This causes the phase field to rapidly transition, to roll quickly between its potential wells, seeking a new, lower energy state. This rapid, coherent movement of the field across vast regions of the cosmos drives that exponential release of energy-converting potential energy, V, and accumulated tension into kinetic energy, the Beck-Giorgi terms, which fuels the rapid expansion. It's a phase transition, a dynamic instability inherent in the field's behavior defined by V, not an externally imposed force.
Incredible. The math literally describes the universe gently beginning, building tension through subtle folds, and then experiencing this period of explosive expansion internally. Now, let's turn to one of the most powerful data sets we have about the early universe, the CMB anisotropies, those tiny temperature fluctuations. The standard model often sees them as purely random quantum fluctuations stretched large. How does this model reinterpret them? As intricate fingerprints of time's very first fractions.
Right. In the standard CDM model, these minute temperature fluctuations, anisotropies of about 1 part in 100,000, or 10 AU Kelvin, are attributed to quantum fluctuations originating in the very, very early universe, possibly before or during inflation.
Tiny quantum ripples.
Yes, tiny quantum ripples that were then stretched to cosmological scales by inflation. And importantly, these are expected to be nearly Gaussian random, meaning statistically uniform, isotropic, lacking any preferred directions or large-scale patterns beyond what random chance allows.
But you're saying they're not purely random in this model. They're more structured, carrying a deeper geometric signature imprinted by the folding process.
Yes, exactly. This model posits that CMB anisotropies are not merely frozen randomness. They carry intrinsic imprints, subtle but potentially detectable patterns of the early rational fractions, like locking in before recombination happened.
How does that work? How do these fractions leave an imprint?
Think of the early universe, that hot photon baryon plasma before recombination, as a vast resonant cavity, like the air inside a drum. When these specific fractional locks occur, they essentially strike this fluid, setting up preferred modes of oscillation, much like a drumhead vibrates with specific harmonic patterns depending on how and where you hit it.
Okay, so the folds pluck the plasma.
In a manner of speaking, yes. They excite specific resonant modes.
What does that look like mathematically, these imprints? How do these specific fractions, like O or O, translate into the CMB data we actually see, like the power spectrum?
The model suggests that the preferred fractions, specifically mentioning O closure, which is naturally associated with hexagonal-like lattices or symmetries, and the half polarity, which establishes fundamental distinctions, gave rise to these natural resonant modes within the photon baryon fluid. These resonant modes, driven by the geometry of the folds, directly correspond to the distinct peaks and troughs we see in the CMB angular power spectrum that missions like WMAP and Planck measured so precisely.
So it provides a dynamic, physical explanation for why the peaks are where they are, and have the amplitudes they do, not just stretched quantum randomness.
That's the claim. It aims to provide a causal link between the fundamental folding process and the specific pattern of CMB anisotropies. Furthermore, this implies that certain anomalies occasionally discussed in the CMB data, things like the axis of evil or unexpected large-scale alignments or specific multipole correlations, might not be anomalies or statistical flukes at all.
They could be real features.
They could be subtle, large-scale alignments reflecting these specific fraction signatures, particularly the earliest ones like half and war. It's the universe revealing its underlying, non-random geometric structure, a cosmic fingerprint etched into the CMB sky.
That's a mind-blowing shift in perspective. So these primordial fractions aren't just abstract numbers in the math. They're actively shaping the patterns in the CMB. And how does this translate into the large-scale structures we see today, billions of years later? Galaxies, galaxy clusters, the vast cosmic web.
Okay, so in the standard view, large-scale structures, the galaxies, clusters, filaments, and voids that make up the cosmic web are thought to form primarily through the gravitational amplification of those initial, tiny, mostly random density fluctuations seen in the CMB. Over billions of years, gravity pulls slightly denser regions together, and they grow.
Standard hierarchical structure formation.
Exactly. Our model, however, offers a more proactive, geometrically driven role for these early fractions. The fractional phase cascades, particularly the later ones, like Or and maybe Or, didn't just create fluctuations. They directly seeded specific geometric domains into the fabric of the early universe.
Like pre-existing patterns.
Yes, imagine large regions with an inherent bias towards, say, hexagonal symmetry from or perhaps spiral structures related to All and the golden ratio. These aren't fully formed structures, but geometric templates or biases. Then gravity acts upon these pre-existing geometric biases, amplifying them, curving them, shaping them into the three-dimensional filaments, sheets, and voids that constitute the cosmic web we observe today.
So it's not just random clumping guided only by gravity. There's a deep underlying geometric template laid down very early on that gravity works with.
That's the idea. It suggests the cosmic web might be less random and more structured, reflecting these primordial symmetries than standard models assume. There's a hidden scaffold influencing where things end up.
So it's not just random clumps pulling together. There's a geometric template, a foundational design from the very beginning. Can you give us the distilled causal chain again? The step-by-step cosmic unfolding from this unique perspective.
Certainly, it's a beautiful, interconnected story when laid out like that.
Let's hear it.
Okay. It begins with smooth. This represents boundless potential, a universe of undifferentiated, calm, pure continuity, no features, no physics yet.
Blank slate.
Then, the first fold, the half-block. This establishes polarity, initiates difference, but gently, without violence. It creates the simplest possible distinction, the first bit of information.
The first ripple.
Next, a cascade of folds. This is the cosmic quake. It rapidly drives inflation through the quick, successive layering of these rational fractions, like O, etc. This generates the enormous energy density and expansion needed for the hot Big Bang conditions. After this initial burst, O closure becomes particularly significant. It suggested this fraction dominates the plasma oscillations in the hot early universe, leaving its characteristic hexagonal imprint on the CMB acoustic peaks, potentially explaining their structure.
The CMB fingerprint.
Then, perhaps slightly later or intertwined, O misfit, related to the Golden ratio, seeds spiral structures. These become the templates, the initial seeds for galaxies and their formations, possibly explaining the prevalence of spiral galaxies in the cosmos.
The seeds of galaxies.
And finally, ongoing folds. The process doesn't necessarily stop completely. Subtle, ongoing folding or relaxation might continue to shape the cosmic web on the largest scales and could even influence dynamics like dark energy, perhaps causing it to oscillate slightly rather than being a pure constant. It shows this process isn't just a beginning, but potentially an ongoing, evolving influence.
From smooth potential to polarity, cascade inflation, CMB patterns, galaxy seeds, and maybe even dark energy.
Wow!
A continuous, interconnected process of cosmic self-organization.
That's the vision, yes. A unified, dynamical origin for structure and evolution.
That's an incredibly comprehensive and beautifully detailed framework, weaving together so many aspects of cosmology into a single, elegant narrative. And the best part, as you mentioned earlier, is this isn't just an intellectual exercise or a philosophical debate.
No, it has to be science.
Exactly. This model comes with a set of incredibly concrete, falsifiable predictions. This is where modern science may be missing crucial clues and where we can actually test this revolutionary idea. This is the exciting part for observers and experimentalists.
This is truly where the rubber meets the road for any scientific theory. If a theory cannot be tested, if it makes no unique, measurable predictions that differ from the standard model, it remains purely speculative, maybe interesting, but not physics yet. This model, despite its profound conceptual shifts, provides very concrete ways for observational cosmology and even laboratory physics to either prove or disprove its claims. That's what makes it potentially powerful.
Okay, let's get into these predictions. Let's start back with the CMB, specifically looking for those residual symmetries, patterns that go beyond what we expect from purely Gaussian randomness.
Right. So the standard CDM model predicts that primordial fluctuations, and thus the tiny anisotropies in the CMB, should be purely Gaussian random. Think of it like perfectly random static on an old TV screen, no overall patterns, equal power in all directions statistically.
Okay, that's the baseline expectation.
Our model, however, forecasts something much more specific. Faint, but potentially detectable scale-dependent hexagonal signatures. These would stem from that aura closure we discussed. And also golden angle spiral phase alignments, originating perhaps from the aura misfit.
Hexagonal and spiral patterns hidden in the CMB static.
Essentially, yes. These subtle, non-Gaussian patterns would be superposed on the nearly Gaussian CMB spectrum. They'd be weak, buried in the noise, but statistically detectable if you know what to look for and how to look for it.
How would we go about testing for such incredibly faint and specific symmetries in a dataset as complex as the full sky CMB?
Yeah.
What would a scientist actually do?
It requires specialized analysis techniques, going beyond the standard power spectrum analysis. Scientists would need to apply specific mathematical filters designed to pick out hexagonal six-fold symmetry or golden angle related to 1.618 correlations.
It's like putting on special glasses to see hidden patterns.
That's a decent analogy. You'd apply these filters to the high-resolution, full-sky CMB maps we have from Planck or WMAP, mapping the temperature or polarization data onto the celestial sphere. Then you'd meticulously search for wind, but statistically significant alignments of phases or correlations between different points on the sky at specific angular scales, multipoles, that correspond theoretically to these Orion-area fractions.
Looking for coherence where randomness is expected.
Exactly. If these non-Gaussian residuals, showing these predicted symmetries, are found at a level beyond what random chance could produce in standard simulations, it would provide compelling evidence for the model. If, after careful searching, they definitively aren't there, it directly contradicts a core prediction.
Okay, prediction 1. Non-Gaussian symmetries in the CMB. What about the cosmic web and large-scale structure geometry? We typically see it as this vast, almost random-looking network of filaments, walls, and voids. Does this model predict something different there too?
Yes. Standard CDM generally treats the cosmic web as emerging from mostly stochastic percolation, a random, statistically isotropic network of filaments and voids that forms as gravity pulls matter together from those initial Gaussian fluctuations. It looks complex, but fundamentally random on the larger scales.
Like a sponge structure.
Kind of, yes. Our model, conversely, anticipates more structured forms underlying that apparent randomness. It predicts hex-biased domains, large regions where the distribution of galaxies or voids might show a subtle preference for six-fold symmetry, reflecting that Ubicon closure, and potentially fuzz spiral filaments or structures forming on the edges of these domains, influenced perhaps by the Ebis fit.
So the large-scale structure shouldn't be purely random, but subtly organized by these underlying primordial fractional geometries, like a hidden scaffold influencing where the galaxies end up.
That's the prediction. It suggests a deeper level of organization than just gravitational collapse of random noise.
And how would we observe these subtle biases in the cosmic web, given its immense scale and complexity? It's not like we can see perfect hexagons of galaxies.
No, it would be statistical. Upcoming galaxy surveys like DEI, the Dark Energy Spectroscopic Instrument, and the Euclid Space Telescope are absolutely crucial here. They will provide vast, unprecedented three-dimensional catalogs mapping the positions of millions, even billions, of galaxies.
Incredible data sets.
Truly. Researchers can then apply sophisticated statistical tools, things like percolation analysis, alignment statistics, topological measures like Minkowski functionals, to quantify the shapes and connections within the cosmic web. They would be specifically looking for an excess of six-fold coherence or hexagonal biases, perhaps in the shapes of large voids or the alignment of filaments within these cosmic cells. They'd also look for evidence of spiralized boundaries or preferred orientations that go statistically beyond what current FISCDM simulations and mock galaxy catalogs predict. It's about looking for subtle, systematic deviations from randomness that align with the model's predicted symmetries.
Prediction 2. Geometric biases in the cosmic web. Next up, dark energy. Orthodox cosmology treats it as a strict cosmological constant, Einstein's A. A static, unchanging energy density inherent to space itself.
That's the standard picture, yes. Characterized by an equation of state parameter WE is E exactly actly. This means its energy density remains constant even as the universe expands, driving the current accelerated expansion. Our model offers a different, more dynamic view.
How so?
Here, dark energy is reinterpreted not as a fundamental constant, but as a tiny residual background of phase tension left over from that primordial folding process, maybe related to ongoing, very slow folds or relaxation.
Leftover energy from the fold.
Potentially, yes, a tiny residue of V, or the kinetic term, and if it's tied to the dynamics of A, it might not be perfectly constant. It could slowly drift or even oscillate slightly over cosmic time. This implies that the equation of state parameter, WZ, could deviate slightly from Mobile 1. Perhaps W is Navier 099, or maybe it oscillates around Navier 1, varying subtly with redshift Z.
But not enough to mess up BBN or the CMB.
Exactly. It would have to be a very subtle effect, primarily noticeable in the late universe when dark energy dominates, without disturbing those crucial early universe anchors. It might even be that these potential oscillations in WS are correlated with the large-scale geometric symmetries, a truly unique prediction.
So dark energy isn't a static, unchanging force, but something with potentially a gentle, evolving pulse. How would we detect such subtle modulations over billions of years of cosmic history?
Detecting such subtle deviations from WS1 requires extraordinary precision in measuring the expansion history of the universe. Future wide-field surveys, like the upcoming SphereX mission with its all-sky 3D map, or continued analysis from DSI and Euclid, will be crucial.
How do they measure the expansion history?
By using standard candles like Type Ia supernovae or standard rulers like baryon acoustic oscillations, BAO, imprinted in the galaxy distribution across a wide range of distances or redshifts, this allows them to map out how the scale factor of the universe, AT, has changed over cosmic time with unprecedented accuracy. This precision could allow us to tightly constrain WZ and see if it truly is constant at Mayday 1, or if it shows any evidence of drifting or oscillating, potentially bounding, or even directly detecting the subtle modulations predicted by this model. Finding WOA1 would be a Nobel Prize-worthy discovery and a huge challenge to the standard TACM model.
Prediction 3. Dynamic, possibly oscillating dark energy. Okay, we also talked about reionization, that crucial epoch when the first stars and galaxies lit up and ionized the neutral hydrogen gas that filled the universe, lifting the cosmic dark ages. Does this model have predictions for the morphology, the shapes of those earliest ionized patches?
Standard models of reionization often treat the growth of these ionized bubbles as largely stochastic, meaning a star or galaxy turns on, and it ionizes a roughly spherical region around it, and these bubbles grow and merge in a somewhat random fashion, influenced mainly by the distribution of the first sources and density fluctuations. The models are often agnostic about any deeper link to primordial symmetry.
Okay, random spherical bubbles merging.
In our picture, however, the idea is that the earliest ionized patches should inherit the underlying geometric biases from the early fraction locks in the phase field. If the matter distribution itself has these hex biases, then the reionization process acting on it should reflect that.
So the bubbles wouldn't be perfectly spherical?
They might show a statistical bias toward, say, hex-like morphology in their interiors, maybe growing preferentially along certain directions related to the underlying structure, or having perimeters that show spiral characteristics. Once you carefully account for the complex physics of radiative transfer, how the ionizing light travels, they wouldn't just be random spheres expanding isotropically, they'd have an underlying geometric preference inherited from the primordial folds.
And we can actually observe this morphology with our current or upcoming technology. That sounds incredibly difficult, looking at shapes from that early on.
It is very challenging, but potentially doable, and it's an exciting frontier. This predicted morphology class can be checked, or at least constrained, using high-resolution imaging from the James Webb Space Telescope, JWST, which is peering deep into the reionization epoch. We can also use 21-centimeter tomography data from next-generation radio telescopes like the Square Kilometer Array, SKA, or HERA.
21-centimeter maps.
Yes, these aim to map the distribution of neutral hydrogen gas during reionization directly. By analyzing the shapes and topology of the ionized regions within these maps, researchers could look for statistical deviations from purely isotropic spherical growth, seeking out those predicted hexagonal and spiral biases. It's pushing the limits of observation, but the potential payoff is huge.
Prediction 4.
Yeah.
Geometric biases in reionization bubbles. This next one is truly fascinating because it brings cosmology right down into the laboratory. A lab-grade falsifier, you called it, connecting quantum mechanics and boundary geometry in a way that standard physics doesn't typically consider.
This is potentially one of the most powerful and decisive tests, yes, because it provides an experimental means to directly probe the fundamental assertion that geometry influences quantum outcomes, rather than relying solely on astronomical observations, which always have more confounding factors.
And standard physics doesn't usually link the shape of the box to the quantum outcome inside, right?
Not in this specific direct way. Quantum mechanics certainly depends on boundary conditions, like confining a particle to a box changes its energy levels, but it doesn't typically predict that changing the symmetry of the boundary itself while keeping other factors constant will fundamentally alter interference statistics or collapse outcomes. Our model, however, asserts that boundary geometry does matter in this profound way. It's tied to how the phase field itself interacts with measurements.
So let me get this straight. We can actually see quantum particles, electrons, photons, whatever behaving differently, exhibiting different interference patterns on a screen simply based on the specific geometric shape of the slits or boundaries in their experimental setup, even if we keep the energy and flux exactly the same.
Precisely. That's the core prediction. Imagine a sophisticated interferometer experiment where you can precisely control the geometry of the boundaries or slits that the quantum particles interact with. The model predicts that if you run the experiment at a fixed flux and energy, simply altering the imposed symmetry, for example, using a setup with asymmetric hexagonal boundaries versus one with asymmetric pentagonal spiral-related boundaries, should predictably shift the statistical distribution of where the particles land on the detector screen. The interference patterns should change in a measurable way that depends directly on the boundary symmetry.
So the geometry steers the quantum probabilities.
That's the geometry picks the rail hypothesis, as it's sometimes phrased in the source material. The boundary symmetry influences the available pathways or outcomes for the quantum system.
Wow. That's a direct, falsifiable prediction that could potentially be tested on a lab bench tomorrow, conceptually at least. If this effect isn't observed, the model faces a fundamental challenge, right?
Indeed. If rigorous experiments show that changing boundary symmetry at fixed energy does not steer interference statistics in the predicted way, it would directly contradict this core geometry picks the rail hypothesis. And since this hypothesis is deeply connected to how the model explains the cosmic initial conditions, the fractional locks acting as boundary conditions, failing this lab test would cast serious doubt on the entire cosmological framework. It's a potential make-or-break test.
Prediction 5. Lab tests showing boundary symmetry affects quantum statistics. Okay, what about the timing of violence? The standard view is bang, instant heat, infinite density. How does this model challenge the timing?
Standard Big Bang cosmology starts from a singularity, an infinitely hot and dense state, violence from the very first instant. This model, as we've discussed, suggests the opposite. The earliest phase, the initial fold from smooth time, what one might colloquially call the bang in this context, was dynamically soft and initially very low energy.
The gentle fold.
Exactly. True violence, meaning rapid exponential expansion and extremely high energy density, the cosmic quake or cascade, only accumulated after several initial gentle folds occurred as the cascade built up tension and complexity. This implies there should be detectable, albeit perhaps very subtle, signatures of an early low-entropy, low-energy state that preceded the main inflationary epoch. It's a quiet buildup before the crescendo.
So rather than an immediate flash from infinity, there might have been a measurable period of calm before the storm that we could actually potentially detect. How would we even look for evidence of a pre-inflationary low-energy state? Inflation is supposed to wipe the slate clean.
Inflation does tend to erase pre-existing conditions, which makes this extremely challenging. However, some theoretical possibilities exist. Perhaps ultra-large-scale features in the CMB or gravitational wave background could retain some memory. Or maybe specific non-Gaussianities generated during the cascade phase differ from those expected from standard inflation models that start hot. If future high-precision cosmological probes, maybe next-generation CMB polarization experiments, or gravitational wave detectors like LISA, were ever to detect unambiguous evidence of such a preceding low-energy, low-entropy state, it would be revolutionary. It would directly falsify the traditional pure singularity initial condition of the standard Big Bang and provide profoundly compelling evidence for this new framework's gentler, more structured origin.
Prediction 6. Signatures of an early low-energy state preceding inflation. And finally, gravitational anomalies. We often attribute these perplexing observations, unexpected lensing effects, galaxy rotation curves, maybe even things like the Pioneer anomaly, to unseen matter clumps. dark matter halos, or even needing modifications to our theory of gravity, like MOND. Does this model offer an alternative explanation for some of these?
That's the standard interpretation, yes. Gravitational lensing anomalies where light from distant galaxies is bent in unexpected ways, maybe creating stronger or weaker magnifications than predicted by simple, smooth dark matter halo models, are typically attributed to unseen substructure within those halos, or perhaps issues with the halo models themselves, or even fundamental problems with general relativity on certain scales.
Right. What's the alternative here?
Our model introduces an intriguing alternative possibility. Some observed gravitational lensing anomalies might actually correlate with the hidden hex domain geometry predicted by this model, rather than solely with unseen matter clumps. If the large-scale distribution of matter, both dark and baryonic, is subtly influenced by these underlying primordial geometric biases, then these biases could, in turn, subtly influence the gravitational field and spacetime curvature in ways not captured by standard models that assume statistical isotropy.
So gravity itself could be revealing those hidden geometric patterns, those cosmic fingerprints you mentioned earlier, through the way it bends light.
Exactly. The geometry isn't just a passive backdrop, it could be an active participant in shaping gravitational effects. Advanced gravitational lensing surveys, which map the distribution of mass, both visible and dark, across the universe by analyzing the distorted shapes of background galaxies, could potentially test this. Researchers could look for correlations between observed lensing anomalies, for example, unexpected shear patterns or magnification peaks, and the predicted locations or orientations of these large-scale hexagonal or spiral domain boundaries derived from CMB analysis or large-scale structure statistics. If we find that some gravitational anomalies align statistically not with expected dark matter distributions alone, but with the specific geometric domains predicted by this model, it would reveal a new fundamental layer of cosmic structure. It would provide strong support for the idea that fractional folding actively influences the gravitational landscape of the large-scale universe. It would be a profound validation.
Prediction 7. Gravitational anomalies correlating with predicted geometric domains. Wow! What an incredible journey through the universe's possible origins and evolution, exploring these fascinating predictions. So, just to recap for you, our curious listener, you've just taken a really deep dive into a cosmological vision where the universe didn't explode from nothing in a singularity.
No singularity needed.
Right. Instead, smooth time folded softly, then cascaded into fractions, each one building tension and complexity. This perspective tells us that cosmic violence grew with each fold, accumulating precisely what was needed for the universe we see today. And perhaps most profoundly, it posits that the CMB, that ancient whisper of the early cosmos, is not frozen randomness,
Not just noise.
but the beautiful, intricate fingerprint of time's very first fractions, a subtle cosmic tapestry woven into the background light.
It's a compelling narrative because it offers, or at least aims to offer, a coherent, self-contained explanation for so many cosmological phenomena from the beginning right through today.
Yeah.
And crucially, it attempts to trade two problematic concepts in standard cosmology: the initial singularity, which is mathematically ill-defined, and the unknown ad hoc inflaton field for a single, potentially testable dynamical object, time's intrinsic phase field.
One field to rule them all.
Well, maybe not rule them all, but certainly to provide a unified origin story. This field, through its early gentle fold and subsequent cascade of fractions, dynamically generates the initial conditions, drives an inflationary phase, and then seamlessly transitions into the hot Big Bang you already know, and for which we have so much robust observational evidence from the CMB, BBN, large-scale structure, and so on.
So what does this all mean for you listening right now? Here's a final provocative thought to mull over. What if the universe, at its most fundamental level, is not just expanding into a static void, but is a continuous, self-organizing unfolding, always new, always evolving, yet fundamentally connected, deeply connected to these primordial fractions, a kind of universal spiral or hexagon etched into its very fabric?
It's a profound thought. Is the universe remembering its origins and its current structure?
And the fascinating thing is, as we've laid out, this isn't just an elegant theory for mathematicians and theorists to debate in academic circles. This is science on the cusp of potential discovery or falsification. With the incredible tools we now have, from full-sky CMB maps like Planck to next-generation galaxy surveys like DSI and Euclid, gravitational wave detectors, and even precision lab-based quantum experiments, the sky and the lab are poised to deliver the answers.
The predictions are there. They are specific, they are testable, even if challenging.
Exactly. So what will those faint symmetries, those hidden geometric patterns, those potential lab results ultimately reveal about our cosmic home? We'll definitely be watching, and we hope you will too. Thanks for joining us on the Deep Dive.